Welcome to the deep dive. So you've handed us a stack of sources, this time focusing on the real technical details of advanced cyber recovery. And our job, as always, is to pull out the essential knowledge for you fast. We want you walking away with more than just facts, really understanding the why behind the architecture.
Yeah, the underlying principles.
Exactly. Today we're getting into secure vaulting, verification, basically what it takes to survive something like a major ransomware hit.
Right.
We're pulling insights mainly from prep materials for the D-PCRT-DY-01 certification.
Which really map out the steps, the requirements for building a truly resilient recovery setup.
It's fascinating stuff.
It really is. And the mindset shift is key here. This isn't your, old school tape backup scenario.
Not at all.
We're talking sophisticated, verifiable, almost military-grade data protection in a way. The sources show how recovery's evolved. It's not just get the files back.
Yeah.
It's about guaranteeing you're restoring clean, verified files. That's the goal. This material basically gives you the blueprint for the security checks, the technical safeguards needed to trust your recovered data completely.
Okay, and just quickly on the source context, these are scenario-based materials, right? Testing how concepts link together.
Yes, exactly. Things like isolation, verification, automated orchestration. They don't exist in isolation. Pun intended, maybe.
Right. So we're going to structure this around what seem to be the three core killers: isolation, immutability, and intelligence. Let's start with isolation, building those walls.
Sounds good. Isolation is foundational. And the big concept here is the air gap.
The air gap. We hear that term a lot.
We do. And in this context, it means the data domain that's the specialized storage holding the secure copies needs to be, well, architecturally separate from the production network.
And the main benefits.
Pretty straightforward. Restricting network connectivity. If ransomware hits your main systems, it just can't reach the vault, keeps the copy safe.
Okay, so the air gap is the design, the disconnect. But then the sources talk about something called the lockdown operation.
Ah, yes. Lockdown.
If you have an air gap, why do you need this extra operational step? Seems a bit like overkill.
That's a really good question. It gets into layers of defense. The air gap is usually about preventing continuous connection. Think firewall rules, maybe a physical network segmentation that only opens up briefly for data transfer.
Right, schedule access.
Exactly.
Right.
But the lockdown operation takes it a step further. Its purpose is to slam the door shut, to close all network access to that vault data domain immediately and definitively.
All access.
Except for the bare minimum needed by the cyber recovery server itself to manage things. It's often done via specific API calls that literally or logically disconnect the vault storage's network interface completely.
I see.
So think of it like this. Air gap is the strong fence with a guarded gate opened on schedule. Lockdown is like hitting a button that drops a reinforced vault door right behind that gate.
Okay. Architectural separation plus an instant operational cutoff.
Yes. That combination gives you total protection, even during those brief data transfer windows. Protects against threats spreading from production if it gets compromised.
Makes sense. Moving from scheduled safety to, immediate total lockdown, that leads us nicely to the second pillar, immutability.
Trustworthiness.
So the data's made it across the air gap, it's in the vault, the door's locked. How do we know, absolutely guarantee, that copy hasn't been messed with? Technically, maybe even legally.
Right. This is where retention lock comes in. That's the specific feature the protection storage uses. As soon as a backup copy lands in the vault and is processed, retention lock gets applied.
And that makes it immutable. What does immutable really mean here? Can someone with admin rights just turn it off?
It means the data cannot be changed, cannot be deleted, cannot be compromised in any way until that retention period runs out. And no, it's not typically something an admin can just easily override. It's often designed to meet strict compliance rules, like for financial records. It ensures that data is trustworthy no matter what happens outside the vault. It's basically the highest level of confidence you can have in that data set.
Okay, so we've isolated it, locked it down, and now made it unchangeable with retention lock. The next step has to be checking it, right? Analysis.
Yes. Checking if it was maybe already corrupted before it even got vaulted.
But if we're analyzing that secured copy, we absolutely cannot risk messing it up during the analysis itself. How is that handled?
This is critical, and the sources hammer at home. When any analysis process runs like CyberSense, which we'll get to the secured copy, must be mounted read-only.
Read-only. Only looking, no touching.
Exactly. The analysis process, whether it's automated or manual forensics, cannot write back to that secure copy. It can't accidentally corrupt it, and critically, it can't be used as a vector to maliciously compromise it. It keeps the clean copy clean.
Right, maintains that chain of trust. Okay, this is where it gets really interesting, I think. Pillar 3, intelligence.
The detective work.
We're analyzing this secured read-only copy for trouble signs like ransomware encryption patterns. We use a tool called CyberSense for that.
Correct.
But before CyberSense can even run, the sources say you must set up a sandbox environment. Tell us about the sandbox.
Yes, the sandbox is crucial. Before you kick off any forensic analysis with CyberSense, you have to configure this isolated compute space, and importantly, it needs dedicated compute resources.
Why not just use spare cycles from somewhere else? Isn't resource cooling normally a good thing?
Not here.
Yeah.
You absolutely cannot share resources for this. There are two big reasons. First, performance.
Okay.
Scanning potentially billions of files for subtle signs of trouble. Entropy changes, weird encryption patterns. It's incredibly compute heavy. Sharing resources would slow down the analysis massively and could impact production stuff too.
Right.
But second, and arguably more important, contamination risk. Think about it. You're analyzing a data set that might be infected. You do not want that analysis environment linked to or running on the same infrastructure as your potentially already compromised production systems. The sandbox is like a biohazard containment lab for data. Keeps everything separate.
That makes total sense. A quarantined forensics lab. So the sandbox provides the safe space, and CyberSense is the tool doing the work inside that space. Where does CyberSense actually live?
The sources are very clear. CyberSense operates exclusively inside the secured vault.
Inside the vault, not in production, not in the cloud somewhere else scanning remotely.
Nope, exclusively inside the vault. It's a fundamental security design choice. You put the analysis engine right next to the data it needs to scan, but keep it totally cut off from the production network by the air gap and the lockdown.
So if the data it's scanning is infected,
the infection, or the scanning process itself, has zero chance of spilling back into your operational network. It stays contained within the secure zone.
Okay, smart. So CyberSense does its analysis in the sandbox inside the vault. What's the output? How do we know if it found something bad?
The key output is the anomaly score.
Anomaly score. What does a high score tell an admin who's maybe desperate to recover?
A high score is a big red flag. It means CyberSense found strong evidence of, corruption, unauthorized changes.
Yeah.
Usually things that scream ransomware or some other malicious attack.
Like what kind of evidence?
Things like mass file deletions, files suddenly showing high entropy, suggesting they've been encrypted, widespread weird metadata changes, patterns that just aren't normal.
And the practical takeaway for the person planning the recovery?
It's critical. This score lets you immediately filter out potentially dangerous backups, instead of accidentally restoring the ransomware infection along with your data.
Which would be disastrous.
Right. You can look at the scores for your backups chronologically. Maybe yesterday's backup has a high score. Okay, let's look at the one from the day before. You keep going back until CyberSense gives you a low anomaly score, indicating a clean, trustworthy copy you can use for recovery. It makes the recovery decision informed and safe.
Okay, that covers the security architecture brilliantly. Let's shift gears a bit to the practical side, the logistics and orchestration needed, starting with planning capacity for that secure vault.
Ah, yes. Capacity planning.
When people plan the size of the vault data domain, what's the common mistake? And what two things must the calculation be based on according to these sources?
Yeah, this trips people up. The common mistake is either trying to back up everything from production into the vault.
Which would be huge and expensive.
Exactly. Or going too small, maybe only basing it on log files or something insufficient. The sources are quite specific. Vault capacity planning must be based on two main things. First, the critical production systems.
The crown jewels.
Precisely. The core data and applications you absolutely need to bring the business back online after disaster. You have to identify and scope that first.
Okay, critical systems, what's the second element?
And this is the one people sometimes forget. Capacity must also account for the required number of CyberSense analytical copies.
Ah, the space needed for those read-only copies used during analysis.
Yes. Remember, you need to mount copies in the sandbox for CyberSense to scan them. You need enough space allocated not just for the retained backups themselves, but also for these temporary analytical copies.
Why only the critical data, though? Is it just cost, or is there a strategic reason to exclude non-critical stuff from the vault?
It's primarily strategic and speed. In a real cyber recovery emergency, You're in triage mode.
Right. Survival.
You only restore what's essential to get the business functioning again. Putting non-critical data in the vault just bloats it, slows down the data transfer into the vault, and crucially, increases the time CyberSense needs to scan the recovery set.
Slows down the verification.
Exactly. Keeping the scope tight on critical assets ensures the fastest possible verification or recovery when time is absolutely critical. And yes, those analytical copies need space too.
Got it. Okay, final stage, orchestration. We've got a clean, verified copy in the vault. How do we automate getting it back to production safely?
Right, automated recovery. For this, the cyber recovery software needs to be able to control the virtual environment where you'll be restoring things.
Makes sense.
So the key step is successfully adding and managing the vCenter server, the one that manages your virtual machines, specifically the vCenter that hosts your PowerProtect Data Manager, or PPDM instance. You add that vCenter as an asset within the cyber recovery software.
Okay, so CR needs to talk to vCenter, which manages PPDM.
Essentially, yes.
Yeah.
PPDM often acts as the data mover, handling the backup and recovery tasks for VMs, and vCenter is the overall orchestrator for the virtual infrastructure. By integrating with that vCenter, the cyber recovery software gets the secure pathway and the permissions it needs to tell vCenter and PPDM, okay, take this clean VM copy from the vault and restore it over here in a safe recovery zone. It enables that automated workflow.
Right, connecting the isolated vault back to the recovery environment in a controlled way. Okay, one last quick nugget, a troubleshooting tip from the materials. If someone's upgrading the software on the virtual appliance that manages all this cyber recovery magic, and the upgrade fails citing insufficient resources, what's the likely culprit? Often overlooked.
Oh yeah, that's a classic. It's usually the simple stuff. The failure is typically because there's insufficient available memory, RAM, or disk space allocated to that specific virtual machine running the management software.
Not enough RAM or disk on the VM itself.
Exactly. Software upgrades often need quite a bit more temporary space and memory than just normal operations to unpack files, run installers, etc. If you haven't allocated enough headroom on that VM, the upgrade process just falls over. Always check the resource prerequisites before an upgrade.
Good practical tip. Thank you for joining us on this deep dive. We hope this breakdown makes these advanced security concepts much clearer and more actionable for you. Definitely explore further.